Okay, so now we want to go on to characterizing magnetic dipole systems. Because ultimately, we have some approximations that take a system out of being a dipole, but if we actually look at that from far away, or do it exactly, we will find a dipole field. So we need something to characterize how strong a magnetic dipole is, because we don't have any magnetic charge. So in electric systems, we characterize the strength of the electric dipole with the electric dipole moment, and we'll have a magnetic dipole moment. We'll use M vector for the moment. This characterizes the strength of the dipole system. Points from south to north. And remember, for the electric dipole, it pointed from minus to positive. The units are amps meters squared. And a compass needle is a permanent magnet, so you could think of it as being a dipole moment vector that's rotating. All right, so the dipole moment's going to produce a dipole field, so if we take the field of a magnet, its moment points from south to north. And you've already measured this in lab. The dipole field here looks like this. Where these will ultimately close in big loops. And you can compare that to the electric dipole field, since this is magnetic dipole. These should be broader, I'm just out of board. To the system you drew with an electric dipole, which we had positive, negative charge on the stick. And then there's my magnetic dipole moment. So you can see outside the dipole, they look pretty much the same. They do close differently inside the dipole because there's no magnetic charge in the system, but there is regions of net electric charge in the dipole system. All right, so ultimately, what a permanent magnet has is producing this dipole moment is the electron spins. The electrons are acting like little current loops. But we can make a magnetic dipole system out of a big current loop. We have a magnetic dipole moment. A current loop. So I brought a current loop. So here is a loop of current. So that's meant to be a current I flowing in my hula hoop like this. So we'll call this a top view. Now I'm going to also tip the hula hoop like this. So what I'm imagining there is the hoop like this. The current's rotating now. Let's see, I tipped it up like this. So it's rotating like that. So it's rotating out of the board here and into the board there. So these are being drawn on the currents flowing around the hoop. Okay. So first, the magnitude of the magnetic moment of a current loop. It's the National Institute of Arts. This is the turns. this is the area of the surface. And by area of the surface, I mean this. So the surface bounded by the current. So we can use the right-hand rule to figure out what's going on. Grab it there. So the field goes into the board inside and loops back around out of the board outside. And we use right-hand rules more here. Let's see that. Now you can see you get a nice dipole field for this current loop, and the field lines point in the direction of magnetic moment, so the moment of that loop is pointing down. We also have a right-hand rule for magnetic moment, but I actually strongly prefer just to draw the field and look at it to see the direction of the moment. So the direction of the moment, so curl fingers in the direction of current. Points in the direction of the moment. All right, so here, current flows like this, moment points in. Here, like that, a moment points down like I drew. And we rotate it up like this so that's all consistent. All right, so now this is the magnetic moment of the current loop, so each of the solenoid current loops has a moment. As we were preparing for the last test, we had just a bunch of loops stacked on top of themselves, and you could figure out the moment of that system. But most of the things you've been dealing with that have magnetic moments are permanent magnets. Like I said, the magnetic moment there is coming from what the electrons are doing. Each electron has its own spin, its own magnetic moment. And in a permanent magnet, the material gets it so all those moments line up. Which is a little weird, right? Because when you measured, when you put two magnets side by side on the rotating stand, the moments pointed in the opposite direction. So something interesting has to happen in the atomic orbitals to get it to be the low energy state that all these electron moments line up. So we also need the dipole moment of a permanent magnet. And there's nothing simple here. There's nothing simple because permanent magnets are weird things. We'll talk about this in a couple weeks. They're generally iron, nickel, cobalt compounds. They're weird mixes. They're tiny bits of one thing and lots of another thing. But the magnetic moment is the magnetization density times the volume. And the magnetization density, just the magnetization, is just the magnetic moment per unit volume. And really, to get this for a permanent magnet, you'd either have to measure it, or you go to the manufacturer's website and they'll report the magnetization density. And they'll probably give you little calculators to let you calculate the field at various points on the surface or the field along the axis. All right, so what happens if I put one of these permanent magnets in a uniform field? You already know the answer to this. I'm going to draw, this is now a B field. Because a compass needle is a permanent magnet, you know that it rotates towards the field. So this magnet would rotate this way. Now, inside the magnets in lab, there's some water, which provides some losses, so it comes to equilibrium along the field line. If there wasn't losses, this thing just oscillate about the field direction. But in a uniform field, there would be no net force. So it wouldn't travel left or right or up or down, it would just oscillate. So the primary thing magnetic fields do to magnets is they spin them. So we have to talk about things whose major property is rotating something. So instead of force, we're going to have torque. So first,